I'll show you a way to do preference fine-tuning and supervised fine-tuning at the very same time. More importantly, I'll show you a way to get better results with this combined approach reliably over supervised fine-tuning alone. The key is a technique called ORPO, which combines cross-entropy loss with consideration of the relative probability of chosen responses and rejected responses. The traditional way to develop a production-grade language model is quite involved. Typically, there are a few big steps. There's the biggest step in terms of training cost, which is the unsupervised fine-tuning. Then there's supervised fine-tuning, where you use a chat format. And then there's reinforcement learning, which traditionally was done by first building a reward model that says which answers are preferred over others based on human annotated feedback. And this was very challenging outside of large companies because developing this reward model and getting reliable results in the reinforcement learning step is not an easy task. Now, things got a little bit easier over the last half year with the introduction of more direct preference optimization approaches. These basically got rid of using a reward model and found ways to directly use preferred and rejected responses in order to align the model towards those better responses. Techniques like DPO, direct preference optimization, IPO, KPO, and others all roughly follow this approach of avoiding the reward model, which helps a lot. However, doing this direct preference optimization step is not necessarily reliable, and you'll see on Hugging Face there are some models where the authors will say, we have just used supervised fine-tuning because direct preference optimization led to a degraded quality of model. What I'm going to talk about today goes even further and gets rid of the direct preference optimization step and the reward model and simply leads you to a two-step approach. First, there's the pre-training with unsupervised fine-tuning, and then in combination, there's supervised and preference fine-tuning. And this is done in a way that I found is more stable as well and reliably allowed me to get results that were at least a bit better than doing supervised fine-tuning alone. So here we are. Today we'll be talking about ORPO, which is an odds ratio method. It's called odds ratio because it considers in this second step here, not just the cross-entropy loss, but the ratio of the probabilities of the chosen, which are the good, to the rejected, which are the bad responses. Just as a snippet of what we're going to see later on, here is the mmlu performance on some models I trained. I trained a Mistral base model, not the instruct model. I trained the base model using this technique ORPO, and independently I trained it with SFT, and I did the same for Tiny Llama, training it with ORPO and SFT. And you can see here that there is outperformance on this benchmark, and I'll show you some more benchmarks in addition later on. So for agenda, I want to recap briefly on how unsupervised, supervised preference fine-tuning work, and I'll describe the ORPO method. I'll talk in particular about how the loss function is computed, because with ORPO you have not just cross-entropy loss, but another penalty term that is related to the odds ratio. Then I'll show you a demo of the fine-tuning by stepping through the notebook, and finally some results comparing SFT with ORPO. To understand preference fine-tuning, it's helpful just to recap very briefly how unsupervised and supervised fine-tuning work. Unsupervised fine-tuning, which is where most of the compute goes in training a language model from scratch, typically involves rather unstructured data. It might be extracts from books or from the internet that are then split into multiple rows. Here I have an extract from Shakespeare that I've split into multiple rows. And there is typically just one column in this data, and each of these columns is fed into the language model. And what you do is you hide progressively portions of that sequence and ask the model to predict the hidden tokens. And by penalizing the model based on what it guesses versus what the actual next token is, you can move the model towards the statistical distribution of the underlying data set. Now, supervised fine-tuning goes a step further and gets the language model into a chat format. This involves having at least two columns of data, and the rows of data are typically conversation style and generated by humans, or sometimes when training smaller models, synthetically using larger models to generate those conversation pairs. For example, you might have a question, why did the chicken cross the road, and an answer to get to the other side, or a question, what is 1 + 1, and the answer is 2. And as I said, this gets the model used to chatting in conversation style and not just continuing on as it might in a long chunk of Shakespeare. Here's where we get to preference fine-tuning, which is the same in terms of goal as reinforcement learning. It's trying to teach the model which answers are good versus which answers are bad. And this is done by having 3 columns of data, but you can also think of it as pairs. The idea is to have a set of prompts, say again, why did the chicken cross the road? But now instead of having 2 answers, have a chosen one, which is the preferred one, and a rejected one. So here the chosen one might be to get to the other side, and a rejected one, because it doesn't follow the joke, is to eat an apple. And the idea here is to shift the statistical representation of the model towards good answers and away from bad answers. So if you have a bad answer here and a good answer here, you're shifting the model in this direction here. Now let's go back and think about how supervised and unsupervised work. They both involve cross-entropy loss to guide the optimization and to guide the model towards the statistical distribution of the underlying training data. So let's consider a simple task where we're trying to predict the next token in the sentence, the God was, and we're predicting the next token here. And let's further consider a very simple model that can only predict 3 tokens, good, bad, and evil. Now, many language models, they have a vocabulary of 30,000 or 100,000 or 200,000, but we're considering a very simple case of just 3 tokens, good, bad, and evil. Now here in the cross-entropy loss case, let's consider an untrained model. So an untrained model is just going to predict the exact same likelihood for each of these tokens, good, okay, or evil. And you can see the probabilities here are 33% in each case. Now consider that what I'll say is the correct answer is going to be good. So the God was good is the correct answer according to that body of text. So in truth, the model should have been predicting with probability 100% the token good and should have been predicting okay and evil with a probability of 0. So the model, when it made its prediction, was under-predicting the likelihood of good and it was over-predicting the likelihood of okay and evil. So what the optimization step does is it moves the model's probabilities so that its prediction of good on the next pass around will be increased towards where it should be, and its prediction of okay and evil will be decreased slightly towards where it should be as well. And this is cross-entropy loss. You can see the mathematical formulation here. You have m, the sequence length, and you have this probability here of the correct token given a certain input. So by looking at the probability of the next token and seeing what that probability is compared to what it actually was, you can make an adjustment to the model through what's called backpropagation and move the probabilities towards where they should have been. Now here's an idea, and this is where you introduce preferences, and this is how ORPO works. Instead of just having a cross-entropy loss like LSFT, which is the standard supervised fine-tuning loss, you add in an additional term here called loss of ORPO, odds ratio. And this loss here will penalize the model if the rejected response, so if the worst response is being preferred over chosen. So if the model is saying that good is 30% and evil is 70%, well, that means the model thinks that evil is the preferred response, which is wrong. So we are going to penalize it because the ratio of that 30% to 70% needs to be flipped to prefer good over evil. Let me just show that graphically. So here again, I have an untrained model that is predicting with the same probability good, okay, and evil with 33.333% chance. And the actual is indeed good. So when you do cross-entropy loss, it's going to consider shifting these probabilities towards where they should be, which is 100% on good, 0% on okay, and 0% on evil. But now that we've added the second term, the loss is further going to optimize the model so that it increases the ratio of the probability of good relative to evil. So if we just did supervised fine-tuning, you might increase the probability in backpropagation by this much. But with ORPO, you're further increasing the probability of good. Whereas in the case of evil, with just supervised fine-tuning and cross-entropy loss, you might be decreasing it to this amount. But because we have ORPO additionally, we're further going to decrease it to extend the relative probability difference between the chosen and the rejected response. And so you can see that with ORPO, there are two things happening. One is we're moving towards the chosen response, but the second is we're trying to move in a direction from the bad responses towards the good responses. The reason why it makes sense to add in preference optimization is clearly illustrated in the ORPO paper by this graph. Here you have the log probability of some good responses versus training step in supervised fine-tuning, and the probability of bad or rejected responses. And if you don't add in this term that maximizes chosen versus rejected, what you'll see is that by fine-tuning on the chosen responses alone, you are also increasing the probability of these rejected responses, because there's quite a lot of correlation between very good responses and only okay responses. So what ORPO does is it not just allows you to follow this chosen path here, but it simultaneously allows you to build a gap between the chosen and the rejected response. Just to summarize, ORPO is a combination of cross-entropy loss that penalizes the predicted versus the actual, and here you want to use your best responses or your chosen, and it adds in this odd ratio penalty, which penalizes the relative probability of rejected versus chosen. So if the model is predicting rejected responses at a higher chance than chosen, it's going to penalize it to try and flip that around. For the notebook run-through, I'm going to be using the Advanced Fine-Tuning repo. You can find out more on trellis.com, trelis.com. Either purchase these scripts individually or buy lifetime access to this repo, to which I'll be making future updates as well. So in the Advanced Fine-Tuning repo, I'm going to go straight to the ORPO branch, which is just being pushed. And I'm going to scroll all the way down to find a one-click template so I can get started in RunPod. So I've clicked here on the one-click template, and that will bring me to a CUDA 12.1 image that I'll be able to run. And if I'm doing Mistral or Tiny Llama, an A6000 is going to be fine. So I'll click on deploy and then continue. My notebook is up and running here, so I'm going to connect to Jupyter Lab. And next I'm going to upload the IPYNB notebook from the Advanced Fine-Tuning repository. I've just uploaded the notebook, and if you have access to the repo, you'll see that there's just one script, but it contains the code for running either supervised fine-tuning or ORPO fine-tuning, both using Hugging Face's TRL trainer. So I'll step through this notebook here now, and if you want more guidance on instructions, you can read through here or in the README within the repository. So first off, we're going to make some installations. Just one thing to note is that it is the developer version of both Transformers and TRL that are going to be installed. So this is why we're using the plus HTTPS GitHub links for both of these libraries here. Now, after the installation is done, we're going to load the model. So here I'm training Mistral, the base model, 7B. There is actually a V02 available now. It's not on Hugging Face, but I believe it's available on Mistral's website. Optionally, you can decide to use quantization if you want to fit on a smaller GPU. For example, if you want to use a Collab notebook. Right here, when you're going to set the data type, if you have an Ampere GPU, one of the newer GPUs like an A6000 or A100, you'll use brain float 16. Otherwise, you'll use float 16, so take out the B. And also you'll have to disable flash attention if you're working in a Collab notebook. So with that model loaded, I like to run some checks. This just tells me that there are no parameters that are on my CPU. Meta device means not GPU. I am going to fine tune using LoRa in the SFT case and in the ORPO case. This reduces the VRAM needed for doing the training. And there are a few different modules I'll train, the attention layers here, and also up and down. You'll notice I've included LM head as well. This is the language model head. Training this helps you to get the chat templating of the model correct. Notice that I'm using a rank of 8 and a LoRa alpha of 32. With that, I'll move on to loading the tokenizer, checking the start and the end token. And next, setting my chat template. Now, the chat template here is actually a little bit custom. One of the key things I'm doing is I'm only including the BOS, which is the beginning of sequence token, this S token here. I'm only including it if there is a user message. So if the chat goes user assistant, it will include the BOS. But if the messages being formatted just includes an assistant message, it's not going to include that BOS token. This is important because we're going to separately format the chosen and the rejected responses. And when we do that, there's not going to be a user message, and we don't want to add an extra beginning of sequence token before the response, because beginning of sequence tokens only generally go at the very start of the entire prompt. So here I've run that and just tested out the template. It is the Llama 2 or Mistral type template. Next up, I set the pad token. It's being set to the UNC token, which is already in the tokenizer. With that, I'm going to turn on the trainability of the embedding and norm layers. So these are layers that you cannot apply LoRa adapters to, but they're important to fine tune if you want to adjust the chat templating. And since we're fine tuning a base model, we do need to do that. The model is not going to be familiar with the chat format we're using, so I need to make these layers trainable here. And this increases the number of trainable parameters. I think it's going to be a few percent, maybe typically in the 1 to 5% range, but it increases the number of parameters beyond if you just do a standard LoRa training. Now I like to build a simple evaluation just to see if the model is performing well. My simple evaluation questions are, what is 1 plus 1? And give me some Python code to add the first 5 Fibonacci numbers. And once I've defined that, I like to actually run the evaluation. And you'll see here how the base model is not familiar with this chat template. When I ask a question, it's just repeating the question. And when I ask for Fibonacci code, it wraps in sol, I presume, for solution. And that actually does give some code here. So not terrible response, but it's certainly not following a clean chat template. Next up, I'm going to load the data set. And this data set needs to have chosen and rejected responses. The data set I'm going to fine tune on is this DPO mix here from Argilla. What's nice about this data set is that it's already got a chosen and rejected response. Just to give you a sense here. So the chosen has got a list of messages, including the question and the answer, and the rejected has got the same question, but it's got a different, worse answer. So we're going to have to extract the prompt from this, and then we're going to extract the chosen messages for the assistant response and the chosen messages for the rejected response. Note that this is created using distill label. It's taking some highly chosen or high quality responses from these data sets here. This does include data from GPT-4, so you might need to consider that if you're going to use models fine-tuned with this data set, because it has implications on the licensing. So here we're going to build the data set, and this script is important because it's going to apply the chat template to each of 3 things. It'll apply it to the chosen text, to the rejected text, and to the prompt. And notice that when we're applying the chat template to the chosen messages, let me just zoom in here a little more. What you can see is that for the prompt message, we're just picking off all but the last message. So everything except the last message we're taking as the prompt, leaving just a response. And then for the chosen and rejected, we're doing the opposite. So we're only taking the last message in the case of chosen and rejected. So just to say that again, we have this series of messages. We want to take everything but the last for the prompt, and we only want to take the last for the case of the responses. And once we have that, we're able to set up a data set that has the prompt, the formatted prompt, by the way, the chosen, and then the rejected. I also then add in an extra field, which just contains a full list of the messages, because for doing supervised fine-tuning, we need a full list of the messages. Next, I like to print each of these. Here's the prompt, and here's chosen. So you can see the chosen answer is B, yes. And then the rejected answer is this one here. And you can see all of the messages just combined in a list here of dictionaries, and that's going to be used for supervised fine-tuning. Now, next I'm going to set some training parameters, and I'm going to keep them the same for supervised fine-tuning and ORPO, so it's a fair comparison. I'm going to train for 1 epoch. This data set has got about 7,000 rows. And I'm going to use a batch size of 16, which I tested, and that fits within memory. gradient accumulation of 2, following my rule of usually having the product of these be equal to 32 as an effective batch size before we do each back propagation. Here I set a fine-tuning tag, either SFT or ORPO, depending on what I'm going to do. Next, I set up a logging callback. This is not essential because I'm going to connect weights and biases. And now I'm going to just clean up the data set for doing supervised fine-tuning. Just to note that here are the two options, supervised and ORPO. For doing supervised, I clean out the prompt chosen and rejected because we just want to focus on the messages. Notice that there's only 6,000 here because I've split off 10% of the data set as a validation data set, which allows us to tell if there's any overfitting. Next here, we're on to the trainer. And if you're using the SFT trainer, if you have your data formatted as messages, which is what I have, you actually don't need to pass in any further information. It will automatically use the chat template of the tokenizer, which has been passed in here, in order to format those messages. Now I'm using a max sequence length of 1,000. This actually might be truncating some of the data, but I'm doing it the same for DPO and for ORPO and for SFT so that I'm being consistent. In terms of learning rate, I'm going to use 1e minus 4, both for ORPO and for supervised fine tuning. I'm using a warm-up. This means the learning rate is lower for a few steps. I don't really think that's essential at all. With that, I run training, and you can see here the results. So the training loss is falling. The validation loss drops from 1.09 to 1.05. And what I do then, I skip ORPO here because I'm doing supervised fine tuning. I save the trainable parameters. These are the non-LoRa parameters. They need to be saved, and I usually push them to the same hub as the adapters. Before then, I do evaluation. And look here how clean this response is. So what is 1 plus 1? The answer is 2. And yeah, by the way, the time for fine-tuning here is about 1 hour and 13 minutes. You can also use unsloth. That would reduce the training time probably by a factor of 2, which is supported in this notebook as well. So here, yeah, we've got some good chat formatting. And here as well, the answer also finishes off correctly in the chat format. So you can see that the supervised fine-tuning is working very nicely. So with that, I would move to evaluation. But first, let me just briefly show you what's different when I run ORPO. And there really isn't all that much different until we get down to the ORPO section here. So instead of running the SFT cells, I don't run the SFT, so I don't exclude any of the columns. And then here in ORPO, I use all of the same parameters. There's just one more parameter here to consider, which is beta. Beta is what I showed as actually lambda. If you remember the loss function, it's cross-entropy loss plus some constant multiplied by the odds ratio. That constant, which was lambda before, or beta here, is 0.2. So this controls how much weight you give to the preference part versus the cross-entropy part. I think 0.5 is recommended, small being 1 billion, although I used 0.2 and got better results than 0.5. And for larger models, maybe 0.1 to 0.2. I used 0.2 for TinyLam and Mistral, and they both worked pretty well. Other than that, everything else is the same. You can see the same learning rates. I'm using 1e minus 4. It is recommended to use LoRa for ORPO, but I prefer to use the same as SFT because that makes it a more fair comparison. So with that, I moved on to training, and there are a few more things to look at in ORPO because you can see you have a validation loss that is progressing, and the validation loss here actually doesn't really change all that much. It's staying around 1.01 in this fine-tuning. And what you're looking at as well is the rewards accuracies. So this is, if you look at, say, 100 pairs, how many times does the model choose the preferred over the rejected, or rather the chosen over the rejected? And so the fact that this is over 50% is a good sign and should be increasing throughout the training. Then I save the parameters and I evaluate after training. And here, there's some warnings, but you can see that this is correctly formatted in terms of responding to the question. And it's also correctly formatted in terms of responding to the code question here. So everything looks good. And I'm set now to move on to evaluation. To do the evaluation, I'm going to use LM Evaluation Harness by Eleuther AI. I'm going to look at a few tests, some quick tests to run, so arithmetic, and also GSM8K, which is a grade school type test. And last of all, mmlu, which is a broader test that takes longer, maybe about 15 to 30 minutes to run. Now, if you're in the advanced fine-tuning repo, which I am here, you'll see there's a file called LLM eval, and this provides you with instructions for doing the install. One of the easy ways to get started is to use, again, a template. So if I use this runplod one-click template, which is set up for eval, it will help me to get started more seamlessly. So again, I would usually run that on an A6000. Let's see down here. And if you look at the customization here, just under environmental variables, it's important to set HF home to the workspace. This is where the volume is mounted, and you want the weights to be downloaded there, because otherwise they'll be downloaded to the container, and that will cause you to run out of container space. So with that, I'll set the overrides and then click on continue and deploy that pod. Now, once that pod is up and running, I'm going to click on connect and just connect by SSH. So I'll copy paste that and head back over to VS Code here. And within my terminal, I'll be able to, I know this will be a bit small, but I can just paste that in and connect to that instance. Now, once I'm connected, there are some installation steps. You can just copy paste here and paste these all in. So here you can see I'm logged in and we'll be working out of the workspace. So I would paste this in and run the installation. And once the installation is done, I've provided a few sample commands here for running different models. Just note that I'm listing the tests I want to run, GSM-8K and arithmetic here. I've also got an mmlu test that's specified right down here. So you can run these tests and they'll run within your terminal fairly quickly, just a few minutes for arithmetic and GSM-8K, but probably about 15 to 30 minutes, depending on the model size, if you're running mmlu. With that, we're back on the slides to take a look at some of the results. So here we have GSM-8K. This is the grade school test, and you can see the Mistral, ORPO versus SFT, so ORPO outperforming a little. Hard to see here, sorry, on Timey Llama, but it is slightly ahead for ORPO. Next up, we can look at arithmetic. And by the way, just a comment here that Tiny Llama really is very bad on this grade school exam. So you can see really the difference between a Tiny model and a 7B model. Moving on to arithmetic, again, you can see that ORPO outperforms in the Tiny model, but actually SFT outperforms a little bit here in arithmetic. Not a huge difference, but yeah, that's definitely going against the grain of ORPO outperforming in this specific case. And lastly, here's mmlu. You can see this is the result I shared earlier. And what you can see is that ORPO is performing better than SFT. And ORPO also in the case of Tiny Llama is performing better as well. Now, there's one other set of evaluations I've done too, which is a more practical set. I talked about it in a video before. It involves using Nicholas Carlini's benchmarking, where he's got a wide assortment of problems and he puts the LLMs to a test based on that. So let's take a look at those results. You can check out the video if you want a guide on how to set them up. And here you can see I've run them for Tiny Llama, ORPO and SFT. Both of these models are performing very weakly here. They're only getting a couple right. I don't think it's statistically significant. There's just one answer right more by ORPO here. Now, next up, here's Mistral Instruct. This is the Instruct model. So I haven't done anything with this. It scores about 5%. And you'll see the SFT model scores 7 and ORPO scores 11. Now, I want to caveat this fairly heavily that these tests would need to be rerun more times. You run into quite a few bugs, I think associated with the model producing outputs that are too long or kind of go on and result in infinite loops in certain tests. So there are certain tests that may be kind of false flags here in that they're failing, but actually they might be passing. So I want to treat carefully the results we're getting here. What is interesting though is that this ORPO model is getting very close to the OpenChat 3.5, which is a CRLHF, so it's a reinforcement learning fine-tuned model using GPT-4 preference data. So it's pretty cool that with just about 2 hours of fine-tuning, this model is able to get up to performance level that's pretty similar to the OpenChat model, and potentially it does even better if I could be sure there were no bugs in running this evaluation. There's one other test I want to highlight, which is I did a run using ORPO with beta of 0.5, and I found that the results were worse than using beta of 0.2, and that was true across the arithmetic and also the GSM-8K benchmark. So I stuck with the 0.2 for doing these evaluation results. Up until now, typically my advice for doing fine-tuning on smaller models is just to stick with SFT. If you look back at my video on DPO, you can even see my performance on DPO doesn't really manage to improve on SFT. And it takes time, it's an extra step. It's hard to know if you're really improving the process. Now I think that this combined approach, doing everything at once, is better. And it seems that it can robustly get better results than just doing SFT. The caveat, of course, is that you do need to have preference data, not just chat data. And so you'll need to come up with some way of either labeling using humans or coming up with a synthetic approach for mapping that data. And maybe that's something we'll look at if people are interested in a later video. In the meantime, I think this bodes well for significantly improving the performance of base models. You can check out the scripts over at trellis.com. That's Trellis with one S. And also I'll drop a few links below. But in the meantime, let me know your comments and questions in the comments section below. Cheers.